As the basics of our gases are very, very important in our thermodynamics, we need to understand how to apply and how to work with typical questions from the laws of our gases, as we know that in actual sense, whenever we are dealing with gases, we are dealing with a gas, actually, it can be expanded, it can actually expand, it can be compressed. That is, a gas is something that is in a form that it can expand or it can be compressed. So what is the idea that we are having here? We are simply saying we have got all right, the gas laws that relates to how this is going to be given. Remember, our gas is given in terms of the volume in cubic meters. All right, in terms, all right, the volume, you can actually use any unit there, but specifically cubic meters. All right, the temperature, that is the temperature there in Kelvin, and also we shall talk of the pressure that is affecting also in kilopascal. So these are the basic units that you need at any condition that you are dealing with a gas. So the laws that we are going to talk about, these are the laws that are going to connect these. It's either connection of the volume, temperature, the volume and the pressure, the temperature and the pressure, any connection that can happen between that. All right, so talking about the laws, we have got the Boyle's law, that is the Boyle's like this. I don't know how to pronounce that one, which is a condition whereby we have PV is equal to C from our engineering science and form. Yeah, I think we talked about that in our science 4. All right, where we are simply saying the volume of a given mass of a perfect gas varies inversely as its absolute pressure, provided that the temperature remains constant. So in a condition that we have of PV is equal to C, we are going to see that there is going to be a change that is happening between the two. All right, this is it, what we have here. So either that we have got, remember we said the gas can expand or it can be compressed. On a condition of an expansion, we shall be starting at this point as one going this side. This is the condition of an expansion, whereby we are having our PV that is equal to C. PV is equal to C. So this is the 0 there, and this will be the 1. Remember your pressure volume. So that means this is V1, and that will be a V2. According to pressure, this will be P1 in kilopascal, and this will be our P2. That's when this is for an expansion. When it is a compression, so this is simply when we are dealing with an expansion. So you see that under an expansion, what is happening here, because we want to consider our Boyle's law that was saying the mass of a perfect gas varies inversely to its absolute pressure, provided that the temperature remains constant. So you will see that in this consideration, we've got two things to be considered. The pressure is starting at 1. This is the higher pressure because this is 0 here. We are going up. All right. This is volume. We are going this side. As we are increasing this side. As we are increasing in pressure, we are increasing this side. So it means we are starting at a higher pressure and we end at a lower pressure when it is an expansion. So it's actually pressure is decreasing, while the volume is increasing. So that's the idea there. The volume is increasing and the pressure is actually decreasing, because this is a P1 here, 1 to 2. So the pressure is decreasing because as you go up, it's a decrease. But as we are moving from this pressure that is here of P1 going to P2, we are opposing the increase that is here having there. So meaning to say, we are talking about what? A decrease. That's a decrease in pressure. All right. And an increase in what? In volume. This is what is happening here. In terms of volume, it's V1 going to V2, it's increasing. But if it is under a compression, you see the opposite. Now, under a compression, we are going to see that this time we are going to start from this point, going this side. That is now for a compression. So we are going to have this as PV is equal to C, not changing, but this is your V1 and that is your V2 now, your pressure also, your P1 and your P2. So you see that in terms of the volume, we are now starting this side going, this is our V1, which is the higher value going this side. So there's a decrease, while the pressure is increasing from P1 to P2. All right, so from P1 to P2, there's now an increase. This is now an increase, and this is a decrease in terms of the volume. So this is a condition when we are dealing with a compression there. So for a compression, you're going to have your typical diagram like that. Okay, so the diagram does not even affect anything as long as you're going to know how to apply your formulas. Yes, the diagram is just there to just show, maybe just want to clearly show your method, like to say, I'm dealing with this, it's a compression, it's an expansion. But we'll see just the effect when you are dealing with the work done. There's another part on its own. But yeah, these are the diagrams. Just need to know it, but does not affect whether you know what is happening. Yeah, no, does not affect anything. What you just need is to understand that these can be related. PV is equal to C under the Boyle's law. What does it mean? It means that at the point 1, I've got pressure and volume there. At point 2, I've got pressure and volume there, which is equal, and so on and so on. So that is the idea that we have, which is equal to a constant. So you see that we are going to have another one which talks about the volume and temperature. This was pressure and volume, which is the Chau's law. All right, so the second one is referred to as the Chau's law. All right, so the Chau's law is stating that equal volumes of different gases expand equally for equal increase of temperatures, provided the pressure remains constant. So thus we have V over T is equal to C. So like I said, guys, we talked about this in our science N4. This is just for you to revise, just for you to be able to answer the question. So it states that V1 over T1 is going to be equal to V2 over T2, and so on and so on and so on, so which is equal to the constant. So this is going at V3 over and so on. So dealing with the stage 1 and stage 2, that is what you need. Stage 1 and stage 2, as we are dealing in this case with the stage 1, stage 2, stage 1, stage 2. That's the point 1 and point 2, where we are referring to either it's a compression or it's an expansion. So that's what we have there. So with this, we are going to see that they can be combined together. What we referred to before as the Boyle's law and what we had from our Chau's law. These two laws can be combined together. So we can have a combination of the two, I mean. So that is combined. All right, combined. So we are going to combine what we had from our Boyle's law and the Chau's law. Okay, so this is, remember this S there, like this. Okay, that is what we have. So all right, so this one we are supposed to have the S first there, then like this. Okay, so this is it. If you take from the first consideration, it was P1 V1 is equal to P2 V2. So already, if you check, this is already occupied P1 V1 P2 V2. So meaning what is just needed there is T1 T2, which is not here if you combine these two. So at the end, you see that this will be P1 V1. Already V1 is already taken there over what? Over T1. So this will be equal to P2 V2 over what? Over T2. So there we are combining the two. So that's what we just have. That's what you need. All right, so we're not going to waste much time. I just want us to check questions. How do they ask these typical questions? On example number 1, we're given a quantity of a gas is expanded. So it's an expansion that is happening, but you're given that what is the pressure at this volume when the temperature remains constant. So when the temperature remains constant, we go back to our part of the laws that we had. Remember, we're talking about the laws. The Boyle's law was stating that the mass is going to be of a perfect gas. It is going to be varying inversely as the absolute pressure provided to its absolute pressure, but provided that the temperature remains constant. So as the temperature remains constant, it means we are simply talking about what? About the Boyle's law. So that's what we simply have in this case. All right. So if it is the case, then it's an expansion. All right. So like I was saying, this part of expansion is just affecting to say from your PV, just going to have something of this nature. Remember, this will be our 0.1 or 0.2. So going down like that. That is PV is equal to C. So whether you know this or you do not know, take your information down. Just take your information. What are we having here? It is expanded from this kilopascal. What is measured in kilopascal from our units? These are the units that we need, remember, from this introduction of our units here. I said you are supposed to know this, but the volume can be given in any unit. The volume, you can work it with any unit, but pressure in Kelvin, where you add 273 to convert to Kelvin. So whatever that is in degrees Celsius, whenever you want to convert that to Kelvins, maybe it's 20 degrees Celsius. So it's going to be 20 plus 273. That will be in what? In Kelvin. So your temperature in Kelvin, pressure, kilopascal. That's it. That's the units that you need there. So this is from where you are starting. You start from, that is your initial pressure. So P1 is 1,700 kilopascal, as we expect that after it has expanded, it is going to reduce. It is starting from 1 to 2, so it is decreasing. All right. So there we are given, and the volume at the same condition at the inlet, we have got the volume 0.085. We are given in cubic meters to air, volume 2. It's from 2. So 2, that is the second one. That is 0.85. That is V2 as 0.85 cubic meters. So the question is, what is the pressure at this volume? So we need the pressure at the second volume, provided that this remains constant. So what is going to be the pressure? That is P2. So from our law, as you can see, that is an expansion, so it's going to decrease. That it just helps you to know how your answer is going to be, but not to say it is going to affect us. No, it's not going to affect us. So from this, we say the product of pressure and volume for the first one must be equal to the product of pressure and volume of the second. So we can use that and find P2. Just divide by what? By V2, both sides. So that means we've got P2, which is equal to P1, V1 over V2. So that is just a substitution to make that you're going to make. That is our P2 is going to be, if you substitute our P1, 1,700 times V1, which is 0.085 over V2, that's 0.85. So that was the idea there. That was just the idea. Then we're going to have our P2, which was 170 kilopascal. All right, just like that. So you just need to know your formulas. So the second part, they are saying here, determine the volume when the pressure is under the same temperature conditions in question 1, under the same temperature, which means what we had before. So meaning to say the inlet that we had is not changing. So we are still at the same conditions that we had before, where our P1 was 1,700 kilopascal and our V1 at 0.085 cubic meters. The only part that changed there is we are now having the pressure now, the second one. So P2 is now at 345 kilopascal. We are supposed to calculate the volume there. That is the condition of our question. So everything from the first part remains constant. What is going to be the volume? So just like what we saw from our PV, This will be P1 V1 is equal to P2 V2. So you can make V2 the subject by dividing by what? By P2. It's just your change of subject there. So that's your V2 P1, V1 over P2. So it's just a substitution there. Our P1, we have 1,700. All right, multiply to V1, that's 0,085, everything over P2, which is 345. So that was going to give us the volume, which is going to be, to 3 decimal places, it was going to be 0,419 cubic meters. That was the case. So you check how you are given. So if we check it was an expansion and we expect that this has to reduce and this has to increase. So if we check, if you have to check here, our pressure in the first place, this was for the first one. The pressure was 1,700, P2 107. It has reduced. That is the idea there. Whereas the volume is increasing. It was 0,085. Now it's 0,85. It's increased. So that's the condition that you just need to know, that it's an expansion, it's a compression. For a compression is the opposite, but that does not even affect anything. Just take your information. If you're someone, you don't even have a problem. So air is compressed at a constant temperature. So you're still having the same thing. That is what the Boyle's law. PV is equal to C. We are given the law that we are going to apply. PV is equal to C. So when it is compressed, we expect that this is going to be increasing in terms of from point 1 to point 2. So we're going to have P1, P2. So the pressure is increasing whilst the volume is what? Whilst the volume is decreasing. That is the case of a compression. So you can even indicate your diagram, which is fine. All right, so that is what we have from this pressure and the volume. So from the pressure of 104 kilopascal and a volume there of 0,7 cubic meters. From 2, this is 1 to another one. The second part, which is our volume, V2, 0.14 cubic meters. Find the pressure after compression. What is going to be our P2? All right, so that's it. So we know that this P2 is going to increase. Remember, it's a compression, but still we have got the same thing at constant temperature. So it follows that P1 V1 is equal to P2 V2. Just like the previous case, we can find our P2 by dividing by what? By V2. So that's P2 is going to be P1 104 times V1 0,7 over 0,14, representing our V2. So this was going to give us our P2 at the end. And our pressure, like I said, it is going to be what? In kilopascal, from the units of pressure, kilopascal. All right? So whatever that you calculate in pressure, automatically it will be in kilopascal. So that was the question, just like that. So you see, that will be the basic part that you just need to know how to relate your points, units. All right. Another part that we are having now, this is the part of the Charles' law. All right. So if you take Y, because we're given that P1 is equal to P2. Remember we said under the Charles' law that equal volumes of different gases expand. They expand equally for equal increase of temperatures, provided what? The pressure remains constant. So provided that the pressure remains constant, it means we are dealing with a Charles' law. So they were given this volume, V1 at the inlet of 10 cubic centimeters and at a temperature of, that is the inlet, which is 100. Like I said, anything in degrees Celsius, you add 273 to convert to kelvins. All right. Anything that is there like that, you have to add 273, that is to convert to kelvins. So this was going to give us 373 Kelvin. Okay. Then another part. Why is it like it's okay? It's fine. I was like, maybe I missed something there. Okay. Then what else? So they say it receives heat at a constant, which is what we we mentioned before, until its temperature is, until it is, that is the second one. So it is at 400. So if we add 273 to Kelvin, that will be 673 in Kelvin. Remember, I said our temperature must be in what? In Kelvins. So the question was, find the change in volume that takes place during the heat supply. The change in volume simply means the final minus the initial. Final minus the initial. So we have the initial volume, but we do not have the final volume, so that we can be able to find what? The change in volume. So thus we need to find first the final volume, which is V2. So in this case, we can find V2 first. All right. So from which concept? We are given volume and temperature. Remember, pressure is constant. So you're going to use the one for V1 over T1 is equal to V2 over T2. That's it. So we can calculate our V2. If I just multiply by T2 here, by T2 here, or I do cross multiply, then divide at the end, it's up to you. So this is going to be equal to T2 times V1 over T1. So that is just a substitution to be taken there. You're just substituting your values. We have our T2, the temperature in Kelvin. So that means our V2 is going to be T2 673 times V1 over T1. So our V1, if you use it in cubic centimeters, it means our V2 is going to be also in cubic centimeters. So that is the idea there. If you use it in cubic meters, it means you're going to obtain V2 in cubic meters. But since this was used in cubic centimeters, we are going to obtain our V2 in cubic centimeters. So that's 18,043 cubic centimeters. Remember, the purpose of finding V2, it is not because we are being asked about that. No, the question was asking us to calculate the change in volume. But we need V2 so that we determine the change in volume, since we said the change in volume is simply the difference that we have between V2 and V1. So now that we have our V2, just a substitution, we got our V2 18,043 minus V1. Remember our initial volume where we started from, it was 10 cubic centimeters. So cubic centimeters, these two can be subtracted for the change in volume. And that was going to give us 8,043 in cubic centimeters also. So learn to answer the question. Answer the question. How is the question given? So the question there was asking you to calculate the change in volume. So for you to have the change in volume, you need the two volumes, V1 and V2. So you were forced now to calculate V2. From V1 over T1 is equal to V2 over T2. You can calculate your V2, then substitute that into the formula for the change in volume. So that is the case. All right, so these are different types of questions that you can have. Another question that you're given is that a gas initially at, so this gas is initially at what? It is initially at 320 degrees Celsius and is reduced in volume by cooling at constant pressure, meaning to say we are dealing with what? V1 over T1, Charles' law, which is equal to V2 over T2. But what is the condition that we have? All right, let's see what we are given here. So initially, it is at this temperature that is at T1. So 320 plus 273 as usual. That was going to give us 593 Kelvin. It is reduced in volume by cooling. It is reduced to 1/3 of its value, which is the original value of the volume. So it means initially our V1 is just V1. That is just V1. We do not know its value. But after everything has happened, they are saying V2, it's a third. It's reduced to a third of initial volume, which is V1. So V2 is a third of V1. So the question was find its final temperature, which is T2. So whenever you're given this type of a question, do not worry that you do not have the volume, so you can't determine the value of the temperature. No, you can, because V2 is given in terms of V1. So these two, they can cancel. As long they are found on the same formula, they can cancel. So remember, in terms of temperature and volume, it follows that V1 over T1 is equal to V2 over T2. I want to find T2, so I can just cross multiply here. V1 T2 is going to be equal to V2 T1. So to find T2, which is the one that I want here, I'm just going to divide by V1. So it means T2 is going to be V2 T1 over V1. So that's what we have there. So the moment you substitute these two now, it follows that our T2, the moment you substitute V2, your V2 is a third of V1. So it was just supposed to be like this, a third of V1 times T1. What is our T1? Our T1 is 593. Everything over V1. V1 is just that V1 because we are not given. It is V2 which is written in terms of V1. So V1 is remaining as it is. So you just see that this V1 and V1 will just cancel. They are the same. So there is nothing there. Just determine your final value for the temperature, which is our T2 was going to be equal to a third of 593. So you're just going to multiply this by a third. So that was the case, just like that. So this was going to give us 197.667 in Kelvin. Just like that. So these are the typical questions. They need you to take this into consideration. Do you understand the relationship between the volumes? So it can be given one volume with respect to another volume. One volume with respect to another volume. The idea there is not changing. No, the idea is not changing at all. If we check another question that we are given, this is now a combination. If you check PV over T is equal to a constant. This is the combination of both. Remember, we said we can combine both our Boyle's law and the Chau's law. So this is actually a combination of both. So a quantity of a gas at a pressure of this pressure and this volume. So we are given the initial condition, the pressure of 1,400 kilopascal, and this volume given in cubic centimeters, which is 20 cubic centimeters, and a temperature of 480 degrees Celsius. So that's 480 plus 273. So you are supposed to add 273, that was going to be 753 Kelvin. It expands according to the law, that is PV over T is equal to a constant to a volume of, to this, that is the final volume of 100 cubic centimeters. So this is cubic centimeters, cubic centimeters. So the volume can be used in any unit as long they're the same. If this is cubic meters, let also this be cubic meters. If this is cubic millimeters, let also this be cubic millimeters. So the effect of volume does not affect anything. When its pressure is, so at this volume, the pressure there is 205 kilopascal. Find the final temperature, which is T2. So as we can see, we've got everything, the pressure, the volume, the temperature. Thus, we can use this formula. Together, we said it simply means P1 V1 over T1 is equal to what? P2 V2 over T2. So I can be able to determine this T2. So it's up to you how you're going to simplify it. Are you going to substitute here, or you're going to make T2 the subject, just cross multiply. That is going to be T2 times P1 V1 that we already have there is equal to P2 that is P2 V2 times T1. So in order for you to determine this T2 that you want, you're simply going to divide by P1 V1. So remove this P1 V1, remove P1 V1. So this will cancel. So that means our T2 was going to be equal to this formula. So you just have to substitute. Are we having P2? Yes, we have got 205 times V2. Remember our V2 in cubic centimeters, that was 100. So 100 times T1, 753 in Kelvin. The temperature is supposed to be in Kelvins. our P1 initially is 1,400 and the volume is 20. So this is 1,400 times 20. So like I said, as long these two volumes are in the same units, it does not affect at all. Cubic meters, cubic meters, cubic centimeters, cubic centimeters, because they will cancel at the end. So it does not affect anything. So that was going to give us the temperature in that case. And this was going to be equal to 551,304 Kelvin. Just like that. Just like that. So you see, that's the combined part. They are combining everything there. It's a combination of both. So you need to know what to do, how to apply your questions. That is how the questions are given. All right. Another question for this was given, I think this is a little bit direct also, just like the previous case that we had. All we need again is to take our information that we are given. So there we are given a tank with a capacity. The capacity is the volume. So initially the volume is 3,4 cubic meters, contains air at a pressure. So this is the pressure of air initially at 690 kilopascal and a temperature of 30 degrees. So if we add 273, that means we're going to have initially a temperature of 303 Kelvin. Water is pumped into the tank until the pressure is, meaning to say the pressure is increased from where it was until it is 815 kilopascal. That is a compression. At the same time, the temperature is raised to, so the temperature initially, remember it was at 30, now it's at 65. If we add 273, it means our temperature, it is going to be 338 Kelvin. So that is the case. So the question is, at a tank with a capacity, it contains this and a pressure, water is pumped until the pressure is, at the same time, the pressure is raised. That is what we have. All right. So, okay. So the question now, all right. So there, the question was to calculate the volume there. All right. We're supposed to calculate the volume there. Calculate the final volume. All right. So what is going to be the final volume? So the final volume, which is V2, as you can see, it's a combination of both V, P, T, Vp, and T. So that means we can use our PV over T. So from the PV over T, it follows that if this is P1, V1 over T1, this will be equal to P2, V2 over T2. So we have to manipulate until make V2 the subject. So if make V2 the subject, you see that V2 is going to give you P1, V1 times T2. Then we divide by T1, P1. So we're going to divide this by T1, P2, I mean T1, P1. So that's just a substitution. We've got our V2. P1, if we have it, 690 times V1, that is 3,4 times T2, which is in kelvins, 338, everything over our T1. This is 303. All right, so our T1 was 303 Kelvin times P2, which is 815. It's all about information, guys. What are we working? We have got everything that is needed there. So this was going to give us 3,211 cubic meters. That is how the questions are given. That is how the questions are given there. So you have to be very, very careful. All right? Very, very careful. So this is it. So this is our V2. So the moment that our question may be asked about the change in volume. All right? So whenever we need the change in volume, maybe this is what we have. So the change in volume will be the final volume minus the initial volume. That is the change in volume. It's going to be the final volume, 3,211 minus the initial volume, which is 3,4. So if I subtract 3,4, I'm going to get a negative 0,189. So when the question is asking you to calculate for the change in volume or for the volume that is being added there to the one that is being, it means this one, a negative, the volume is reduced. So thus the volume was reduced, all right? The volume was reduced by 0,189 cubic meters. Remember, this volume was in cubic meters before. So they can ask such questions. You are supposed to be careful. How do you attempt your questions? So these are the questions that you're going to have. So you shall have our next class, whereby we shall talk about the processes that we have, the isobaric, the isochoric, the isothermal processes, the polytropic, the adiabatic. How are they related and how do they differ from each other? Talking about the heating of gases, also calculating the work done. That is the major part that you're going to have. So make sure that you become part of the family, Mason African Motive, so that you do not miss all those classes that we shall have. But for now, that's it. Till we meet again.